I thank to the organizers for giving me this opportunity to upload my talk slides. I believe that many of the audience already heard about this Hall viscosity in the context of quantum Hall systems. A few years ago, I introduced the Hall viscosity in the context of magnetic-skyrmions by generalizing the so-called quantum field theory Wada identity with the topological skyrmion charge. Today, I would like to show that this Hall viscosity can be a significant part of the Hall transport of skyrmions. This talk is mostly based on the paper to be published shortly in Physical Review Research. I would like to start with one experimental fact that is not very well known. Recent Hall transport actually show that there is an asymmetry between the skyrmion and anti-skyrmion Hall angles. The top two figures are the magnetization upstate with lighter color inside the magnetization down background with darker color under the electric current. The bottom two figures are the magnetization downstate inside the magnetization upstate. The authors identify them as half skyrmion and half anti-skyrmion. It is not surprising that their Hall angles are opposite to each other. What is surprising is the difference in magnitude of the angles. The top one has about 35 degrees, while the bottom one has 31 degrees, with more than 10% difference. Once you realize you want to search out to find other similar experimental data. Yes, there is at least one more, probably many more. Many of you are already familiar with this paper, which is one of the first papers that directly show the skyrmion Hall effect. On the right portion, we see that the Hall angles are different for skyrmion and anti-skyrmion. Similarly, in the left portion, if we combine those data, you can see that their difference is a little bit less than 10%, but still it's significant. As far as I know, this asymmetry cannot be understood by known mechanisms. In this talk, I hope to offer an explanation for this asymmetry by introducing the Hall viscosity through a transverse velocity component of skyrmions in the DL equation. Throughout the talk, I assume that there is no asymmetry between skyrmion and anti-skyrmions in pinning effects, internal degrees of freedom, forcing mechanisms, and so on. First thing I want to do is checking the direction of this Hall viscosity. According to the Kubo formula that is developed around 2012, it is proportional to the 2 stress energy tensor. Using a typical Lagrangian, we can check that the Hall viscosity is an even function of magnetization vector n, while the topological charge is an odd function. So the direction of the Hall viscosity is independent of skyrmion charge and depends on the direction of the flow. In the paper, we also show that the direction is actually transverse to the flow of motion. As we know, skyrmion and anti-skyrmions are pushed toward the opposite transverse directions, as in the left figure. It turns out that they are actually pushed toward the same transverse direction as in the right figure due to the Hall viscosity. If we combine these two effects, we can actually illustrate the situation as follows. Now we see that the skyrmion has a bigger Hall angle in pictorial way. I was not particularly concerned with the beginning motion in the left side. If there is no pinning effect, skyrmion and anti-skyrmion move in a straight lines there as well. In the rest of the talk, I will focus on TL equation that is described the motion of Skyrmion center. Small n is a normalized magnetization vector, and ms is the saturation magnetization. TL considered the center of Skyrmion with capital Xi that is moving with the velocity vi. The corresponding TL equation is described by three terms. The first term is Magnus force that is proportional to the Skyrmion charge Q. The second term is total dissipative drag term that is independent of Skyrmion charge. And the last term is related to external force that includes various spin torques. Initially, I tried to understand the effect of Hall viscosity or the asymmetry I talked about in the drag force term. When I consider the circularly symmetric Skyrmion configuration with an angle phi and integer m that is related to the topological charge, the dissipative drag contribution is actually symmetric, and so it is parallel to the forcing direction. So that means that it does not produce transverse motion nor the asymmetry between the Skyrmion and anti-Skyrmion. It took a while to figure out a different way to incorporate the Hall viscosity in TL equation. I added the transverse velocity component as Rij, which is R times epsilon ij. Time derivative is proportional to the spatial derivative, so the generalization to the TL equation is straightforward. And it is consistent with the TL's initial conditions, and I expect that the internal force, anisotropy, exchange energies, and so on would not contribute as initially TL described. This generalization describes completely different Hall angle, Hall dynamics. The first new term is proportional to the Skyrmion charge, and this Hall viscosity component is actually parallel to the forcing direction. The second new term is transverse to the forcing direction and is independent of Skyrmion charge. This universal transverse drag term is originated from the Hall viscosity. Assuming the forcing direction is along x coordinate, we can solve the generalized TL equation. The second one actually gives us the Hall angle. We see that it depends on the Skyrmion charge, Q, and Hall viscosity R. When R vanishes, it reduces to the usual Skyrmion Hall angle, and Skyrmion and anti-Skyrmion have the same Hall angles. Now, let's apply this to the experimental data. As we already mentioned, there is an asymmetry Hall angle data for the Neal type half Skyrmion and anti-Skyrmion that utilize the spin-orbit torque in ferrimagnetic film. In Hall angles, forcing mechanism and spin-orbit torque turn out to be not important for Neal type Skyrmions. We compare the Hall viscosity contribution compared to the Skyrmion Hall effect as like this, and to my surprise, the Hall viscosity is about 5.4% according to our analysis. This is actually a significant part of a Hall transport. When I drive this one, I assume that the universal transport drag contribution is solely from the Hall viscosity, and I also assume that pinning effect, internal degrees of freedom, shape deformation, and system-specific forces adapted in the paper are the same for Skyrmion and anti-Skyrmion. We also check various spin torques, spin orbit torque, spin-Hall torque, spin transfer torque, and emergent electromagnetic fields, they do not actually change the result. In fact, the last one might enhance the contribution of Hall viscosity. So our result is actually understated. We also visited the other paper and estimated the Hall viscosity contribution, which is about 3%, and still it's very significant. I will finish my talk by mentioning that I think it is much more clean to see the effect of this Hall viscosity in the antiferromagnetic materials. The conventional skyrmion-Hall effect is absent. Nevertheless, skyrmion and anti-skyrmion will experience the same transverse motion due to the Hall viscosity. They have the same direction for both skyrmion and anti-skyrmion. Maybe we can call this as Hall viscosity angle. Thank you very much for your attention.